Hello, this is Diego. I am going to show the results of the rerun of the Ethiopian bell season trend analysis. Let's take a look. So the main question was, this was asked by Camonix a few years ago. Are there any changes in rainfall patterns during the bell season? We're going to examine the last 39 years now. And we are using improved rainfall using GeoClim for 140 stations, most of the time 140. There were many times that were only 50 stations. Decadal values from 1981 to 2019. So the main thing that we're going to do is analyze changes in the start of season, the duration of the season. Is the season getting shorter or longer? And is it starting later or earlier? And also how much the rainfall total has changed during the season. So this is the average rainfall for the belt. This is the variability. Again, this is from February to June. This is the coefficient of variability. This is the trend using the GeoClim trend function. So we see clearly the difference, mainly during the belt, in the belt regions. And here is change or trend using the comparison of averages, the average of 1981 to 1999 compared to the average of 2000 to 2019. Is showing that this region is decreasing while this region is increasing. This is comparison of the same averages, 1981 to 98 and 99 to 2019. So in this case, we are using the 100 millimeters intervals to see how much change there is between the two averages. We see that this area of the 300s is shrinking in the latest average. The area of the 400s is shrinking even more. The area of 300s is disappeared right here. So this is clearly showing us that there is some change in the rainfall for that season, for the February to June period. Here we are seeing it at the 300 millimeter intervals, where we see this is the 300s is shrinking a lot. This area right here is disappearing or completely disappeared. So this is a way to show the change. So in this map, we are putting together the red area is the 1981 to 98, and the green area is 99 to 2019 average rainfall. So we see how much it has shrunk. So this is a way to look at this, just to get an idea if there have been any changes. But then we're going to go into a little more detail in looking at the start of season, the end of season, and the length of season. So to do this, then we divided the bell season into two, the agropastoral areas and the pastoral areas. And we did this in order to determine how much rainfall is needed to start the season. So in the agropastoral areas, we use the WRSI rules that it is 25 millimeters for the first decade and 20 millimeters for the next 2 decades. And then we defined that the first decade as the beginning of the season. And for the pastoral areas, then we use the 10, 10 and 5 to start the season. We're going to start looking for the start of season on decade 4. Then we find 25 millimeters or more, and then we find 2 decades that add up to 20 or more millimeters. Then we say that this is the beginning of the season. In order to identify the end of the season, we find the first decade that is lower than 10 millimeters. And we start looking after that and making sure that there are at least 3, so more than 2, less than 10, then is telling us that this one is the end of the season. Based on the beginning and the end of the season, then we identify the length of the season. And so this is the length of that season for that year. Then we identify the total rainfall for the season. In order to do this, it was very difficult to add up the seasonal total rainfall. But then what we decided was to just calculate the rainfall from the 4th decade to decade 18, consistently through all the years. So these are the things that we're going to look into: the start of season, the length of the season, and the total rainfall. Let's take a look at how all these different parameters were calculated. So for a given year, in this case, we are dealing with a pastoral area. So we're looking for the 10 and 5. For a given year, we start looking for the start of season at decade 4. Then if we find a decade with 10 millimeters or more, then a potential start of season. Find 2 more with 2 decades with 5 or more, then we say that this one is the start of season. So here we calculated the start of season, decade 8. Then we start looking from decade 18 up, the first or the last decade with less than 5 millimeters is this one. So here is where the season ends. That's decade 15. So then here we are saying, okay, so the decade started in decade 8, the season started in decade 8, ended in decade 15, length of season 7 decades, and the total rainfall then is calculated from decade 4 all the way to decade 18, consistently throughout the years. So that is the way we calculated that. Then here we have the first plot that we have is for the start of season. That is this plot right here. This is telling us if the season is starting later or earlier. Then this plot right here, this one is the length of season, and the red bars are the seasonal totals. Then calculate the slope for each of those, and that's what we are going to map. Something important down here is when we calculate the total rainfall for the season, then this one is the median for all those years in this polygon. Then calculate the change in those 39 years. This is the change in in millimeters. And down here we calculate the percent of the median that change means. So this one is the change in percent of median. And this is very important because that's what is telling us how much rain we are either losing or gaining. So let's go back to the PowerPoint and take a look at the maps. This map right here is showing the change in the start of season in terms of a number of decades. The positive numbers are telling us that the season is starting later. So this is 3 decades later, almost 4 decades later is starting. And here is just starting a few days later. Then we move to the length of the season. The length of the season is telling us that positive numbers is telling us that the season is getting longer, and negative numbers is telling us that the season is getting shorter. So in number of decades. So these regions right here are losing 4, 3 decades, and so forth. So these regions are losing almost a month, and these regions haven't changed much. Then comes the change, the percent of change of the seasonal median rainfall based on this February to June rainfall total. So what we're mapping right here is how much of the median is that change that we identified. So what we are seeing here is that these regions are losing 63%, 55% of the median, 26, 34. So we're seeing here that all these regions are losing a great amount of rainfall. These regions right here are gaining rainfall. So we see that here, this region right here, I think this is a data problem. If we want to take a look at some of these areas, we could just click right here, and these are the plots that I was showing in the Excel. So we see how the start of the season, so the season is starting later, and here is showing that the length of the season in blue is going down, and the total rainfall is also going down. And this is the long-term average for that specific polygon from January to June. So this is the seasonal profile. This is the analysis that we just did for the fall season. I finished doing it again. I did all the calculations again to make sure that this is pretty much what we got the first time, but I wanted to do it again just to make sure that there were no big mistakes. So if you have any questions, just let us know.